Welcome back everybody to another video lecture from Miss Semino. Today this is going to be the fourth video in our thermochemistry series, and we're going to be talking about Hess's Law today. So our specific objectives are state Hess's law of heat summation and describe how or why it is used in chemistry. So we're really just doing this to measure our enthalpy changes, and it's just a little addition, subtraction, flipping some equations around. It's really not that hard. So as I just mentioned, we need to go ahead and solve these equations with further enthalpy changes using Hess's law or standard heats of formation. Hess's law is very important in thermochemistry. You can see it's been around for a while, since the 1840s. Here's a picture of Hess himself, and what it says is if you add two or more thermochemical equations, remember those are those equations that have like the energy added to either to the reactants or the product side, they're going to give you a final equation, and then you can add the heats of the reaction to give you the final heat of the reaction. And so this is called Hess's law of heat summation, but we're often only going to refer to it as Hess's law. So as I mentioned, Hess's law is not hard to do, but there's just a few rules that you need to know. So if we're looking at this equation here, we've got our hydrogen, 1/2 oxygen yielding water here. We can see that it is going to produce 285.5 kilojoules of energy. And so notice it's a negative, by the way. But if we were to flip this equation around and put our water in the front and have our water be decomposing into the hydrogen and oxygen, notice the value stays the same, but the sign is flipped. So if you turn an equation around, you can change the sign to get the same amount of energy, but in the opposite direction. If you multiply the equation by a number, you must multiply the heat by that number as well. So here's our equation again. Notice there's a 2 in the front, so all they did here with the value is they just took this value and they just multiplied it by 2. Or you can just leave the equation as it is. So when you're doing a Hess's law problem, if you can leave the equation as it's written, that's ideal. If you need to reverse it, just go ahead and switch the sign for that heat or enthalpy change, and then increase the coefficients. This is your third option in the equation, and increase the heat by the same amount. So you'll sometimes see us talk about the standard heats of formation. So the delta H for a reaction that produces or forms 1 mole of a compound from its elements, its standard condition. Remember, standard condition is a little bit different than STP. It's at 25 degrees and it's still at 1 atmosphere, but our temperature is different. The symbol that we're going to see here is in black. This is more of like a, should be more of like a degree symbol there. So this just means our standard. And then the standard heat of formation of an element in its standard state is arbitrarily set to 0, and this goes for diatomic elements as well. So remember, chemistry honors, we're using a different textbook, so we're not going to have these pages. But basically, the heat of reaction can be calculated by subtracting the heats of formation of the reaction from its products. And so these are like in tables that we will find in our textbook, or they'll be given to you on the worksheet. But the basic idea here is that you're going to take your delta H of your products and subtract your delta H of your reactants to find your heat of formation. So here is an example problem. So calculating the standard heat of reaction, and so the question's asking what is the standard heat of reaction for the reaction of carbon monoxide with oxygen to form carbon dioxide. So we want to list our knowns and our unknowns. So from the table that is in your textbook or online given from the worksheet, you would get these values. Notice that oxygen in its diatomic form has the 0 kilojoules per mole because it's a free element. Your carbon monoxide is going to have a negative 110.5, and your carbon dioxide is going to have a negative 393.5 kilojoules. And so what we're looking for is the overall delta H, or the heat of reaction. So what we want to do is we need to write our equation. We need to balance it, and so this is what our balanced equation is going to look like. We want to go ahead and we want to figure out what our heat of formation of our reactants are, because remember that equation is you take your products minus your reactants. So let's just go ahead and look at the reactants. We have 2 moles of our carbon monoxide, and so we know that that is going to equal negative 110 kilojoules per 1 mole. We've got 2 moles here, so the moles are going to go ahead and cancel out. And we've got the 0 kilojoules over here because we've got that oxygen. So then we find that our delta H for our reactants is negative 221.0 kilojoules. Then we need to find it for the products in the same way. So we have 2 moles of carbon dioxide. So we're going to take our 2 moles and here's our negative 393.5 kilojoules. You do the math on that, the moles are canceling out, and that gives us a negative 787 kilojoules. So I just moved the slide up. Remember that the equation is you take your products minus your reactants. And so here's our products minus our reactants, and we have an overall heat of reaction of negative 556.0 kilojoules. So that means that when we convert our carbon monoxide to carbon dioxide, it is releasing 556 kilojoules of heat or energy. I like this slide. I think it does a little bit better job explaining about like what's going on. So notice here we've got our methane plus our oxygen yielding carbon dioxide and water. So hopefully you guys remember that that is a combustion reaction. So if we look at the heat of formation for our methane, we can see that we have this value. Our heat of formation for our oxygen, again, since it's in its elemental form, is going to be 0. Carbon dioxide, and here's our water. So remember, we're going to take our products over here minus our reactants. So our first product is carbon dioxide, so here's our value for carbon dioxide, plus, notice we're doing 2 of the waters, and that's because there's this 2 coefficient here. Okay, so notice they're in the brackets here. So this is all of our products minus our delta H, or enthalpy change of our reactants. And so the 74 is coming from our methane, and then oxygen is 0. So then when you do the math on this, you find that it has an enthalpy change of negative 802.24. And then the question is this endothermic or exothermic? Remember, if our delta H is negative, it's going to be exothermic. So it's releasing heat, and this makes sense. It's a combustion reaction, so most likely we're burning something, and so heat would be released. Well, that's all I have for thermochemistry. As always, make sure you write down any questions that you have. Make sure you're working through all the example problems, and see me before school or after school if you've got questions. Thank you. Bye.